In this module, let's look at how tools calculate cell delay. In this module, you'll learn to identify the cell delay information that comes from the libraries and also how these table lookup models are used to calculate the cell delay. As we saw before, each cell has one or more timing arcs, and each of these timing arcs have a delay associated with them. And so the propagation delay through the cell is commonly known as cell delay. So we calculate cell delay based on the intrinsic delay of the timing arcs, what load it's driving. So basically we measure the output load, and then based on that load we actually determine the delay of the cell. And also what is the input transition. Sometimes input transition and input slew are actually kind of interchangeably used. And basically we're using the input slews or transitions to calculate the delay through the cell. You can break down cell delay into transition times, intrinsic delay, and propagation delay. So transition time is when the pin actually has to change states from low to high or high to low. That is considered transition. And intrinsic delay is the delay of the cell when zero signal is applied, and basically no transition time and there is no output load, and that's when intrinsic delay is measured. And finally, propagation delay is the total delay between when the input signal changes state to when the output changes state. So that whole thing is considered as the propagation delay or the cell delay. The propagation delays are measured from when the input threshold fall percentage point to the output threshold percentage point. So if you say 50% of the input signal change has happened to 50% of the output signal change has happened, then that could be considered as the cell delay. If you look at the libraries, these input threshold percentages and output threshold percentages are given for both rise and fall. And so therefore, depending on what the input signal is doing and what the output signal is doing, we basically measure the delay from the input signal to the output signal based on these percentage thresholds. So in this example, we are measuring the cell delay from 60% of the input to 40% of the output, because the input is actually measured with 60% and the output is measured at 40%. Each cell in the library has the model for that particular cell, which defines what the cell footprint is, what the area of that cell is, and basically what are the pins, what are the directions of the pins, what is the output function, and any delays associated with that particular cell, and any transition times and power dissipation, what are the yields. I mean, you'll see a lot of different data for that particular cell in that particular cell model. There are two main models for lookup tables. One is called the two-dimensional lookup table, which uses the input slew and output load to determine the delay. And then there is the three-dimensional lookup table, which uses the input slew, the output load, and also the related output load as well. So if there are multiple outputs, so what is the load as seen by the cell for pin Y, for example, and then there is another pin Y bar. and both of these are outputs, and in which case the related output is actually uh, for the y bar, what is the output, what is the delay at the output y based on the delay of output y bar. These are what you would see as the lookup tables, and um, you also have all the timing arc information for all the inputs to outputs, what is the output function. So all of these different things are actually listed, and the lookup tables, the accuracy of it depends on the accuracy of the SPICE simulations. And so because these models require very few variables, they're very easy to calibrate. And these library characterization teams create these cell models for you to actually use at different slew and load variations. And they're plugged into your .libs or the Liberty library models, and that is what you would use in your static timing analysis. Here we show an example of a 2D lookup table model, and if you look at the .lib or the library itself, the slew is actually plotted on the y-axis here, and the load is plotted on the x-axis. So index 1 would then be the load, and index 2 would be the slew. And so for an example, for a slew of 1.05 and for a load of 0.3279, it's showing 0.3643. So you would actually determine that based on the lookup table, and that's what the tool will also do. In a 3D lookup table model, you also have the related output load as seen by Q, and so therefore that Q bar, whatever the loading is or Qn, the loading is actually applied, and thus calculating the delay at Q. So this illustration here basically shows the slew axis and the load axis and load 2 axis, and for this lookup table, the related output pin capacitance or net capacitance is used as two values. And so once you locate the slew and load for the third one, we use the load 2 and thus calculate the delay based on load 2. And if the delay doesn't fall on any one of these load points, then basically what the tool does is it interpolates the values and thus coming up with the final number for your cell delay. Try the following activity to reinforce your learning.